We will now understand on the same grounds how to go ahead with the stick diagram of NOR gate. So using the same methodology as explained earlier, you will have to generate the schematic of a NOR gate. So once you reduce the expressions using the truth table, you will get 2n in parallel and 2p in series, which is the representation for NOR gate. And let us, or directly we can go into the layout representation rather than going into the stick diagram. So on the same grounds, so directly I will go with the layout representation. What is the first step? The first step is to draw two metal lines. So the metal line representations are shown as horizontal lines. So this is how we have the metal representation. And since we are to represent the CMOS pull up region and pull down region, this is anyway optional. Next, polysilicon is what you have to do. Two inputs A and B. So you have two inputs A and B. So this is the gate which has the connection, and go ahead further in understanding how the source and drain terminals of PMOS and NMOS are connected. So this is your P diffusion on the top. This is your P diffusion, and in the bottom you have N diffusion. Now, however, by this time, by merely practicing again and again, you will get to know which are the terminals which has to be connected to VDD or VSS, where you have to give the input, where you have to give the output. So A, let me take, what is it? Normally it is the PMOS source which is connected to VDD. So let me call this as source, and this as drain, and this as source, and this as drain. So on the top regions they are connected in series. I will extend this line and using a metal representation, and this becomes your contact. This becomes your contact. Next, source drain, they need to be connected. Right, metal line. They are connected using a metal representation, and this is the drain where you have to take the output. So just leave it. We'll later on associate with this is where you will get a contact, and this is called as Y. Next, bottom. Two sources are connected to are connected to ground. Two drains are connected at the output. So let me call this as drain. Let me call this as drain using metal. Let me draw it neatly. So this is your drain. This also is your drain. This also is your drain. Everywhere it is connected with a metal representation. See this connecting tappings. So finally understood. This is your drain. This is your drain. Two sources. No other choice. You have to take a loop and you have to come down here. Take a loop, come down here and extend here. This becomes your contact for source. So this is your source and this as well is your source. So use the metal representation. Fine. So this is the representation for a NOR gate. We'll now understand how to do the schematic and the layout of a compound gate. So when do we call it as a compound gate? when you have a combination of multiple logic gates. For example, you have an expression here y is equal to ab plus cd whole bar. So this is a combination of AND gate, OR gate and a NOT gate. So combination of three gates, we can call it as a compound gate. For example, you have an expression and this is the associated schematic for this. So how exactly should we represent this or demonstrate this? Please notice when you have an expression y is equal to ab plus cd whole bar, you can have two types of expressions. One is of the form given here. This is one form, and the other form is you can have the same expression as y is equal to ab plus cd. So these are the two expressions. What is it you observe in the first expression? Y is equal to AB plus CD whole bar. This expression is represented in active low. This is represented in active low. Why do we call it as active low? Because it has a bar. It has a bar. It is not logic and we consider this as active low. And this is not having any bar over here, not complementing. Therefore, this is in active high. This is the first observation we are supposed to do, whether the expression given is in active high or in active low. Second step, once you realize whether it is an active low or active high, next step, if it is in active low, this is the rule. If it is in active low, you have to realize first is important. You have to realize first in NMOS and then in PMOS. First in NMOS and then in PMOS. Vice versa. If you have an expression as shown here, then you have to first realize this in PMOS and then in NMOS. So any one rule you remember and the complement of that will be the representation for active high. Now I want to get a structure like this. So in order to get a structure like this, same expression, what is it you have to do? As we have already discussed, that you have to first analyze this in NMOS. So I will analyze first in NMOS. What is it in NMOS? You see A dot B. What is the representation of dot? It is in series connection. So I will have A and B in series. And I will represent their inputs as given by the equation. This is NMOS. Why should we do it in NMOS? Because it is in active low representation. In that A and B are in series. Therefore, A and B are in series. C and D is also in series. But this whole C and D and A and B are in parallel because there is a plus symbol. So, in parallel, this is what I am doing and the inputs are C and D. So since I am representing it as NMOS, obviously the bottom terminal will be connected to VSS as shown here. So this is what is the bottom terminal. This is my NMOS. So as a ground rule, we know what is connected to ground in NMOS. It is the source. It is the source of two transistors. Since they are connected in parallel, two sources together can come here and it forms. Next, since they are connected in parallel, obviously, okay, let us see that later. And this is where we take the output. Okay, this is where you get the expression. Because if this is represented in NMOS, the pull-up region is represented in PMOS and which is reverse. Now, what do we do? So you have identified this as source, or if you want you can identify now itself that what is this? This is your drain. Since they are connected in series, if this is drain, what should be this? Series means it is source. If this is source, what should be this? Drain. And what is the key rule? Where is the output taken? Output is taken at the drain terminal junction. Now we'll represent PMOS. What is PMOS? A and B in NMOS, if they are in series, A and B are in parallel. A and B are in parallel. Call it as B. Call it as A. So A and B are in parallel. And ground rule, we know that this will be your VDD. So A and B were in series in NMOS, now they are in parallel. C and D were in series, now C and D also will be in parallel. And AB is in parallel with CD. So AB is in series with CD. So you have the series combination, you have them as. So now you can call this as D, you can call this as C, and join them. What is this? This is your output. So what is the terminal? Outputs are taken at drain. So first step is drain. They are connected in parallel. Drain and drain are connected together. They are connected in parallel means this is also source, this is also source. They are connected. This whole thing is in series. So this will be drain. If one is source, the other one will be drain. So you have your drain. And the other terminal is source. So source of PMOS is connected to VDD. So this is how we get the schematic representation. How do we go with the layout diagram? So you have 4 inputs here. These are your metal representations. These are your metal representations. Sorry, it's come out here. These are your metal representations. Next, 4 polylines. 1, 2, freehand sketching, so the quality. So this is your polyline. Name them as A, B, C, D. And you have diffusion lines. 1, 2, 3 and 4. Similarly, 4 diffusion lines. You can notice here if there is no proper spacing, there is a possibility of short. So we need to have the proper spacing between one polyline to another polyline. That is one of the ground rule used in layout design. We will see that later. Okay, now A, B and D. B and D source are shorted. You can have this. B and D are shorted to source. B's drain and D's drain are connected to A source. B's drain and D's drain, they are connected to A and C, A source. Okay, this is B's. Similarly, D's source is connected to here, C, direct connection. Then C drain, this is what is left out, is connected to A drain. Take it here, loop, A drain. This is what is your output Y. Next in the top, A and B are connected to source. A and B are connected to source. You have a contact. You have a contact here, square contact. Color it. Okay. A drain and B drain. A drain and B drain, they're shorted. A drain and B drain. Here, take a loop. It's connected. A drain and B drain are connected here. Next, this in turn is connected to C source. I can show here, connected to C source and D source. And D drain and C drain here. So I will have to do the loop over here. So this is one shorting between D drain and C drain. That is C drain and D drain. And loop and a loop and a loop and here. So this is your final output. This is how a logic representation, schematic representation and layout diagram for a compound gate is done. Y is equal to, okay, this is one more, you can do it as an exercise. This is the representation. So you can look into this directly. What is this? This is your active law. If it is an active law, I have to represent first in NMOS. So how does it look in NMOS? A plus B plus C, plus is there. So A, B, C are in parallel. That is what is shown here. And there is a dot with D. So this whole three parallel combinations are in series with D. Got it. Next, that will be complementing in PMOS. So in PMOS, what is it to observe? ABC, which were in series, which were in parallel in NMOS, will now be in series ABC. And ABC is in series with D. ABC is in parallel with D. So this is the representation of signal or an expression Y is equal to A plus B plus C D whole D bar. Now let me take an example of an expression Y is equal to A plus B C. This is an active high signal. So when it is an active high signal, what is the first step? You have to realize this in PMOS. So what is PMOS? What is B and C? B and C is in series. I have B and C in series. B and C in series. This whole thing is in parallel with A. Done. So done with PMOS representation, and this becomes your VDD. Fine, no worries. This is your PMOS. Now let us go with the NMOS representation, and I'm showing it in different color. B and C were in series means how will B and C be here now? B and C will be in parallel. So this is C and this is B. So B and C were in parallel with A, they will be in series with A. That's it. The output is this. Y is equal to A plus BC. So this is an active high representation Boolean expression. The same thing can be realized using layout representation. If ever you want to check whether this acts as this, one thing you have to first analyze the truth table. What is the truth table? when you have 3 inputs, how many states you will get? 2 to the power of 3. So you will have 8 states. And how are the 8 states represented? 0 0 0 0 0 1 0 1 0 up to 1 1 1, and subsequently give the combinations. So ultimately what is the combination? A plus BC. So B into C plus A. Whatever is the logic, that logic you should get here. When you analyze either NMOS or PMOS with respective to inputs, you have to get that representative logic. And one more thing, what is the representation? As already told, Y is equal to A plus BC. A plus BC is in active high. This is one more rule I forgot to tell in the previous slide. So when the representation is in active high, the inputs should be shown as active low. So this is how the representation for Boolean expression with active high symbol looks.